Hello, I am Mladen Čičić from KTH, and I'll talk about how we can use connected vehicles for sensing and actuating the traffic flow. Now, the reason why you might want to apply traffic control in the first place is usually so that you can decrease some congestion. And typically this comes down to decongesting some bottlenecks. If the bottleneck that we're dealing with is recurrent, such as ones caused by a lane drop or an on-ramp or a merge, then we've been using classic Eulerian traffic control for quite some time to deal with this problem. And I say Eulerian meaning the ones that use fixed sensors, such as inductive loops, and fixed actuators, such as traffic lights or variable speed limits. However, if we're dealing with a non-recurrent bottleneck, such as the one caused by, for example, a traffic accident, then the control problem is a bit more difficult because typically we will not have all the required equipment in place. And in this case, we benefit greatly from using Lagrangian traffic control, meaning ones that use mobile sensors and mobile actuators. In particular, mobile sensing has been on the rise lately. Well, let's just say your favorite navigation app probably does not use inductive loops as a data source. And while this approach certainly does have its pitfalls, the potential for using connected vehicles for traffic control is certainly immense. And you don't even need these connected vehicles to be automated, because most of what we're trying to do can be achieved using just a simple app. Therefore, the question that we're trying to answer in this work is how can we sense and control the traffic flow using only some connected vehicles? More specifically, the problem that we'll be looking at here is stop-and-go wave dissipation using connected vehicles as both sensors and actuators. Since a stop-and-go wave's discharging flow is typically lower than the road's capacity, you may think of them as sort of a virtual bottleneck. We'll be looking at the homogeneous stretch of road without any on and off ramps with stop-and-go waves entering from downstream. Now, stop-and-go wave dissipation is a well-known problem, and typically what you want to do is you want to delay the inflow into the stop-and-go wave, restricting just the right amount of traffic flow until the stop-and-go wave is dissipated. As in our previous work, we'll be using the connected vehicles as controlled moving bottlenecks. However, the difference here is that now we are assuming that we only know the traffic density close to probe vehicles that we are using for sensing. But first, the traffic model we'll be using is the well-known cell transmission model, where we split the road into cells and then track what happens with the traffic density rho inside each of them. We'll be using the triangular fundamental diagram and extending the CTM to implement capacity drop and also to allow the free flow speed inside each of the cells to vary in time. By doing this, we use a neat little trick where we can model the influence of moving bottlenecks and stop-and-go waves as long as we know their position and movement on the road, which we can track externally. So namely, we use UI to force the traffic density to converge to the reference density profile, which correctly models the influence that a moving bottleneck and a stop-and-go wave have on the surrounding traffic. So the situation that we're studying looks something like this. Plots like this show the traffic density heat map with hotter colors indicating higher traffic density, and we have space on the horizontal axis and time on the vertical axis. You can see that at some time, indicated by the dashed black line, we have the stop-and-go wave enter this road segment from downstream. We indicate the trajectory of an actuator vehicle that we can control in red, and you can see that if we don't apply any control action, this stop-and-go wave will simply continue existing. Instead, what we want to do is use this actuator vehicle as a controlled moving bottleneck to dissipate the stop-and-go wave. Now, if we know the discharging flow at the stop-and-go wave and the overtaking flow at the actuator vehicle, then it is pretty simple to model the evolution of the number of vehicles in the zone between them. Similarly, if we know the speed of the stop-and-go wave and the speed of the actuator vehicle, then we will know how the distance between them will change. Now all we need to do is ensure that there are no vehicles left in the zone as the distance between them approaches 0, which yields this reference speed for the actuator vehicle. Now, if we assume that we know the traffic model, then all of these parameters will be known except rho bar, which is the average traffic density inside the zone. Of course, if we know the traffic density profile everywhere, then it is really simple to calculate rho bar. But the question still is, how do we get rho I, the traffic density profile? Well, if we don't know the traffic density profile rho, best we can do is use its reconstruction, rho hat, based on whichever measurements we have available. And now we assume that we only know the real traffic density in these cells that are within the sensing range of the probe vehicles, and elsewhere we will just update the reconstruction based on the traffic model. For the initial densities and the info to the first cell of the road segment, we can use some mean values based on historical data. You can see the comparison between the real traffic density on the top plot and the reconstructed traffic density on the bottom. You can see that until one of the probe vehicles, whose trajectories are shown in bright green, enters the stop-and-go wave, we don't have any idea that there is a stop-and-go wave there. Another thing that is interesting to note is that while these probe vehicles are in free flow, we get very little new information as they go along the road, and that is because they're traveling along the characteristic lines of the PDE, which describes the traffic model. However, as they enter congestion, we are now intersecting the characteristic lines and we'll be getting more data that is relevant outside of the immediate vicinity of the probe vehicles. So based on the fact that we don't benefit at all from probe vehicles in free flow, you might ask whether we can reduce the communication burden without sacrificing reconstruction quality by deactivating them. On the right you can see the traffic state reconstruction using all available probe vehicles, whose trajectories are shown in green, and an actuator vehicle shown in red. And on the smaller plot, you can see what happens if we deactivate all the vehicles, who are then shown in black. Now, if we apply a simple probe vehicle activation scheme, you can see that the traffic state reconstruction doesn't change at all. So what we are doing here is we still have a smaller subset of all available probe vehicles that will always be active, because we need to detect the stop-and-go wave and other congestion somehow. But then we only activate those probe vehicles that we predict are about to enter congestion, so that we get more information about the congestion, and then we deactivate them again once they've left congestion and gone back to free flow. Based on this selection scheme, the set of currently active vehicles can be defined like this. Here, delta is the range at which we activate probe vehicles. To illustrate how the full control loop works, here's a step-by-step example. First, we have an actuator vehicle run into the stop-and-go wave, detecting it. Then we activate additional probe vehicles to gather more information about the stop-and-go wave, while an upstream actuator vehicle starts restricting the overtaking flow. After some time, it will be able to dissipate the stop-and-go wave, and then finally the following actuator vehicle will dissipate the congestion left in its wake. Notice that the following actuator vehicle actually restricted too much of the traffic flow, which was because the actual inflow into this road segment was lower than what we predicted. Now, we will also be using the no control case and the full information control case, shown in the smaller figures, for benchmarks. Finally, we wanted to study what impact availability of probe vehicle has on control performance. We simulated a 5-kilometer stretch of the road and added connected vehicles to its origin according to a Poisson arrival process, with the average gap between two connected vehicles being g. When we add a connected vehicle, we say that with probability pp, it will be an always active probe vehicle with probability PA, which we set to 0.3 in this case. It will be an actuator vehicle, or if it's neither an actuator vehicle or an always active probe vehicle, it will be an inactive probe vehicle. We conducted 100 simulation runs using different combinations of G and PP, and as performance metric we use the delay ratio of each control case compared to the no control case. We compared 3 reconstruction-based controls using all available probe vehicles as probes, which is shown in yellow. Then using the probe vehicle selection scheme that we just described, shown in red. And then finally using only the always active probe vehicles, shown in blue. The full information control case is also shown in purple and is given as a benchmark here. Unsurprisingly, as you can see, the control performance deteriorates as G increases, so as we have fewer and fewer connected vehicles. But note that a gap of 2.5 kilometers on a 5-kilometer stretch of road is quite severe, so it's not surprising that we're hardly able to be better than the no control case, because typically we will not have enough time to dissipate a stop-and-go wave after we have detected it. Also, when the average gap is small, we do approach the full information case. And you can see also that in all cases, the adaptive probe vehicle selection scheme was able to improve the performance compared to the case when we always use the always-on probe vehicles. To conclude, the question that we wanted to answer in this work was how can we sense and control the traffic flow using only some connected vehicles? And I hope I have shown this on an example of stop-and-go wave dissipation using connected vehicles as both sensors and actuators. We have seen that the reconstruction-based control approaches the full information control as more and more probe vehicles are added, and we can also employ an adaptive probe vehicle selection scheme to reduce the communication burden without sacrificing too much of state reconstruction performance. For future work, here we assume that the traffic model was entirely known, which is a pretty bold assumption, and we are currently working on relaxing this assumption and learning the traffic flow model as we reconstruct the traffic state and apply control all simultaneously. Another interesting question that one might ask is how does controlling actuator vehicles and probe vehicles affect the traffic state reconstruction quality? And one might even think of a way of optimally controlling probe vehicles in order to ensure best possible traffic state reconstruction. And then finally, here we use the very simple probe vehicle selection scheme, and one might think of many other more complicated and better selection schemes to use. So with that, I would like to thank you for your attention and answer any questions that you might have.